Hello, my name is Michael Simpson, and I'm a professor in the Environmental Studies Department at Antioch University's New England campus. And I wanted to welcome you to the second course in our series on climate resilience. In this course, we will look at how scientific information can help move community action. In order to do that, we need to build a stronger foundation of understanding of climate variability, how to take action in the face of uncertainty, how a community must balance risk in regards to action or inaction. And we'll end the course with a discussion of the role of science and scientists in policy decisions. A great resource for finding additional information on topics touched upon over the next 4 weeks can be found at the Center for Climate Preparedness and Community Resilience. There you'll find informative webinars, research reports, and proceedings from our biennial national conference that the center puts on. FYI, the next one will be in the spring of 2020. Now, what am I going to cover in the specific recording? Well, the basic understanding and the development of what we call global circulation models and aspects of uncertainty with projecting future climate. But we also will talk about climate as a system and how they're reinforcing our positive feedback loops. And then we'll touch upon possible outcomes due to inaction of not using science to drive policy making. Now, there's a broad scientific consensus that climate change is occurring and is human caused. In the recent past, this has reached the media and informed the citizens that scientific papers normally do not reach. But even this week, there's still voice denial that climate is changing due to human causes. In parallel to this, the Union of Concerned Scientists is raising the alarm about a marked increase of an attack on the science itself. There is a groundswell of science deniers, and this reaches the levels of officials in the current presidential administration and the 115th Congress, where one is seeing a conscious dismantling of science-based health and safety protections, the sidelining of scientific evidence, and actually an undoing of recent progress on scientific integrity. So how much consensus exists within the scientific community to support the conclusions that human-caused greenhouse gas loading is and will be impacting global climate? A recent study examined 12,000 peer-reviewed scientific papers in the climate science literature and found that these papers stated a position on the reality of human-caused global warming. 97% said it happened and is happening and at least partly human cause. And firstly, what percent of the American public understands the scientific consensus that is held about human-induced climate change? Only 13%. But there is scientific consensus, so why has it become so difficult for this scientific message to stem a call to action at the local level? Well, let's put ourselves in the place of a local decision maker, an elected official. There are multiple stakeholders or multiple needs that need to be met by a community. And there's expectation that local officials will spend tax dollars wisely. Now, when we consider risk from climate change, it's a combination of the likelihood or probability of future climate mediated impacts combined with what is the scale of the impact. And this is often translated as cost to a community. These together is the risk facing the community. The science can definitely inform the first aspect of this algorithm. But again, the elected official looks at the likelihood of something occurring as uncertainty, about something that seems separated from them by time and space from their day-to-day decisions on how best spend taxpayer money. When there is pressing needs for schools or fire trucks or building another wastewater treatment facility, they are very concerned about spending money in error. So what becomes risk in this regards is risk from uncertainty. As we approach the climate scientists' projected future, the uncertainty about that future will diminish. However, as we will discuss later in this talk, the cost of damages will significantly increase if action is not taken. Now, most of you have heard that we had a meeting in Poland. It was known as the 24th meeting of the United Nations Conference of Parties, often called COP24, where almost 200 countries came together to draft a policy on how to meet the goal to avoid the loading of greenhouse gases so that the average global temperature stays below 3.6 degrees Fahrenheit or 2 degrees Celsius. Prior to COP24, the fifth assessment report released by the United Nations International Panel on Climate Change, the IPCC, reports there is a continued increase in global greenhouse gases in the atmosphere, and there is a concurrent continued increase in average global temperatures. And this was a major source of tension at COP24 due to the decisions by countries in COP23 in Paris to reduce greenhouse gases. Now, the validity of this report, it can be based on that it was authored by over 830 scientists or experts from more than 80 countries. And the scientific conclusions of these scientists had been peer-reviewed over time by approximately 30,000 additional scientists. And so the report had stated that unless we meet the pledges to cut CO2 emissions that were raised in the Paris Accord, global warming will reach 5.4 degrees Fahrenheit or 3 degrees centigrade by 2100. And why this is important is that scientists feel that this will cause a bifurcation or a threshold cross where there will be a tipping point where the permafrost in the northern latitudes will thaw, which could drive global temperatures uncontrollably higher. And so, without the full involvement and alignment of our technical, social, and political dimensions, we won't even meet the 2.0 degrees centigrade goal. So as more syntheses of future trends are published, there's a continued improvement in how projections are considered, where the consensus of a particular projection from multiple scientific studies is high and the amount of evidence supporting it is robust. Thus, the IPCC is looking at evidence in the upper right-hand corner. Now, there was a released report in October, right before the Poland meeting, called Global Warming of 1.5 degrees centigrade. And they were basically projecting what the impacts would be if we capped at a 1.5 degrees centigrade or a 2.7 degree Fahrenheit versus going all the way to a 2 degrees centigrade or a 3.6 degree Fahrenheit. And as you'll see highlighted in red here, their recommendations are peppered with probability modifiers, which reflect the certainty or uncertainty associated with any future projections. These uncertainty or certainty modifiers first are considered confidence modifiers. So a very high confidence, at least 9 out of 10 chance of being correct. But they also have a likelihood scale. So they're something that is very likely, in this case they use the word extremely likely, is close to 100%. Okay, greater than 90% probability. Extremely likely is a greater than 99% probability. But there's never 100% certainty about future projections. So how do we make decisions without 100% certainty? Well, it is probably a valid assumption that interpretation of the past has less uncertainty than projections of the future. And the evidence shows, either through direct measurements or proxies that are strongly correlated with carbon dioxide concentrations in the atmosphere, that there has been a significant loading of greenhouse gases since the advent of the Industrial Revolution. And as the curve shows, the rate of loading is increasing at an increasing rate. So if the lead scientists of the UN and the fifth assessment report are saying it is almost certain that humans are a major contributor to increasing the global temperatures, what they are talking about is what I hope you learned in your earlier education, that there is a greenhouse gas effect that occurs when greenhouse gases are loaded into the atmosphere. Solar radiation can go through these greenhouse gases and basically hit the ocean or the lower atmosphere or the land, and is re-radiated as heat radiation. And it's this heat radiation, as it moves back towards space, gets trapped by these gases, resulting not only in warming of the Earth's atmosphere, but the oceans as well. But we're seeing from the data that the warming in the atmosphere is not equally distributed around the world, with the northern latitudes seeing a disproportionate amount of change. And as ocean temperatures have risen, it has been observed that there is an increased melting of the Arctic Ocean sea ice, which seems to be an increasing trend over time. Now, with the loss of reflective ice, or what we call the albedo effect, and the corresponding opening of greater areas of ocean water that now can absorb the non-reflected solar radiation that once reflected off the ice, and it transfers from solar radiation to heat energy, which warms the ocean. Now, this sets up a reinforcing or positive feedback where the ocean warms faster. resulting in more Arctic sea ice melting, which means less reflectance or albedo of solar radiation, which increases the warming of the Arctic Ocean, and so forth and so on. And it also should be noted that as the atmosphere heats, it causes more water to evaporate into the atmosphere, which will lead to more frequent and more extreme precipitation events around the globe. Now, this excessive water vapor in the atmosphere can also act as a heat-trapping gas, which could create another reinforcing or feedback loop, which could speed the change in global temperatures. But this dynamic can be complex, since a thick cloud cover also increases upper atmosphere albedo at the top of the clouds, which then reflects more solar radiation back into space. So what are the other greenhouse gases? The major players are carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons. The amount of each gas in the atmosphere has an impact on global warming, which is considered the radiative forcing of the gas or the climate forcing of the gas. Technically, this forcing is the difference between sunlight absorbed by the Earth and energy radiated back to space. This radiative forcing is reported in units of watts per square meter of the Earth's surface. And many factors affect the change of such climate forcing over time. In trying to grasp the heating of a particular greenhouse gas, we look at three factors. First, the amount of loading of a particular gas into the atmosphere. And obviously, we want to look at this rate over time. Second, it's the relative global warming potential or the climate forcing of a particular greenhouse gas. And this is set up as a relative scale where carbon dioxide is considered a 1 in forcing, and the other gases are related to that amount. Finally, we want to know what the lifetime of the gas is in the atmosphere. So in order to reduce the greenhouse gases, often a term called climate mitigation, we need to identify how such gases are being generated. And then we try to find a way in which to reduce the amount of greenhouse gases come from these sources through technological change, substitution change, and change in behavior. Now, projecting how the future greenhouse gas generation may be, the IPCC developed a range of future projections based on possible societal behavior. The pessimistic view is business as usual as we're doing today. However, there is a much more optimistic pathway for increasing greenhouse gas loading. The future societal behavior is broken into environmental standard operating procedures and new technology, economic practices, projected population growth, and what scales these would be applied, whether at the global or regional scale. And they came up with a storyline for each of these of what the future may be based on the decisions by policymakers and the behavior by citizens. More recently, the IPCC has called these things representative concentration pathways, or RCPs. They came up with 4 major pathways selected for climate modeling and research, which describes different climate futures, all which are considered possible depending on how much greenhouse gas is emitted into the atmosphere in the years to come. As you see here, there are 4 RCPs, and they're labeled after a possible range of radiative forcing values in the year 2100 relative to pre-industrial values. So you have a 2.6, 4.5, 6.0, and 8.5 watts per meter squared, respectively. So how are scientists translating the projected loading of greenhouse gases into atmospheric parameters that result in climate change, such as changing the global temperature or changing global precipitation trends? Now, this is based on physics of fluid dynamics, energy absorption and transfer. But a good conceptual image is that the scientists look at a column of the Earth's atmosphere, and then all the way down to the Earth's surface and down into the ocean depth. They slice this column the way a CAT scan images the body. And in each slice, there are dynamics that occur that are both contained within that slice and relates and communicates to the adjacent slices. And over time, more and more factors have been looked at that impact how each of these slices will respond to greenhouse gas loading. Now, these columns are laid out in what is known as a Gaussian grid, covering the entire Earth. The early global circulation models were quite coarse, so that each column covered a very large area on the Earth's surface, and did not take into account the changes in a number of variables over space. Over time, the granularity of these models have been improving. This shows the resolution of the analysis that has improved from the first assessment report, FAR, to the 4th assessment report. You can see the resolution of the ability to see how changes occur at a much smaller spatial scale has improved. The 5th assessment report has reached a spatial granularity of 70 kilometers by 70 kilometers. And scientists are now downscaling these global circulation models to a local level. And the resolution is getting much better, to the point that communities can take the information and incorporate it into their planning and decision making. There are a number of these downscaled analyses, often at the state level, that provides the specificity and it identifies potential impacts facing a particular community so that decision makers can change policies on how to respond to this changing climate. This is an example of a downscaled model done by the scientists at the Center for Climate Preparedness and Community Resilience. It's a study conducted in Western New Hampshire with funding from NOAA. Future global circulation model projections for precipitation were downscaled using the data from climatic data centers proximate to the study area. And within the circle of blue, there is a high degree of certainty that the projections are likely. In order to provide that certainty, any model needs to be validated so that possible projections have a certain level of certainty that decision makers can use. So in the Southern New Hampshire study, historic precipitation data was taken from 1924 to the late 1950s and put into the model so to project what the precipitation data would be from 1970 to 2000. When the actual, here with the circles, was projected to the model, which is basically the hatch or square line, we saw on average only a 3% variance between modeled and observed. As such, this model then took 1970 to 2000 data to project mid-century 2100 to project what precipitation would be in this region. Now, back to the projections of future temperature trends. As you can see, there are a number of what we call centers around the world with supercomputing capacity to assess all those variables in each of those slices in the vertical grid from the atmosphere deep into the oceans. Now, prior to 2008, they had all their own procedures to make future projections. And as such, the further you got into the future, the higher the levels of uncertainty, and once all these models diverge. But over time, one did see the projections from the different GCMs begin to converge. But still, there was a broad range of possible climatic impacts from the different center models. But looking at this curve, one might at least say that the various models seem more congruent in the trends up through the end of the last century. But still, if we take a closer look at those models before 2000, and looking at historical data, there was variation among the GCMs in regards to the point where global temperature crossed the threshold from a more linear increase in temperature, that is temperature increasing at a constant rate, to a more exponential trend with temperature increasing at an increasing rate. The different global models basically looked at this bifurcation occurring at different times in the historic data. So, at a 2008 meeting involving 20 climate modeling groups from around the world, the Working Group on Coupled Modeling was created to develop standardized modeling protocols and procedures. What you see here is the result of that. This is known as the Coupled Model Intercomparison Project, and this is the 5th iteration, or CMIP5. The different CMPI5 curves reflect projected future climate forcing possibilities. The dark curve is observed data. Now, what we see here from this is the trends infer that we do have time, albeit a short period of time, to correct our future path before the trends diverge. But you will also notice that once we are on a chosen path, due to the behavior of greenhouse gases in the atmosphere, coupled with positive or reinforcing feedback loops that are initiated, it becomes increasingly difficult to reverse direction and get on a path that will minimize the future cost to society and the natural world. Now, remember that the past, our society's systems, our infrastructure, was actually created in a world of uncertainty. But we have had faith in our licensed engineers to adequately design what society depends upon. So, for example, When there is a new culvert or bridge put in, we do not question its ability to pass a peak flow. But to design such water conveyance infrastructure, the engineer needs a specific value for precipitation, which drives runoff, to put into their calculations so to size infrastructure. The precipitation amount is known as the design storm rainfall amount. It has been based on data collected over time and statistically analyzed by scientists. This map shows historical rainfall amounts for the design storm engineers used to put in New Hampshire's water conveyance infrastructure at stream crossings. But if we look at the certainty we place in our licensed engineer designs from a scientific perspective, the statistical analysis of historic data gives us a range of possible future values with a certain confidence interval. The range does not support the assumed certainty in an engineer's design value. So we have lived with this uncertainty in our infrastructure every time an engineer's design was accepted by a community. And realized during over that time in which engineers were using design storms, the statistical analysis of those storms have changed. Our approach to addressing potential uncertainty in the scientific information that is presented to us is that we should embrace it. That is to avoid specific predictions of the future, but to show what the alternative future possibilities may be based on what society decides. Scientists characterize this as a scenario analysis and not projecting a single future, but a possibility of futures based on human behavior. Example of this is a NOAA-funded study that scientists did in Minneapolis to determine to what extent Minneapolis's storm sewer infrastructure would be under capacity based on a range of future possible precipitation scenarios. The red in these maps indicate where the stormwater system will lack the resilience to handle such future storm runoff. The scientists did not say what the community should do, just what the impact would be if a certain precipitation future occurred. The scientists also coupled the projections about the underside infrastructure based on potential futures with actual storm events that had been observed in the historic experience of the audience. That was to ground them in what the projections meant in regards to actual risk. The y-axis on this graph is the percentage of stormwater components undersized for specific precipitation events on the x-axis. Now the blue areas indicate the statistically downscaled scenarios of projected precipitation based on a changing climate. The red arrows indicate actual precipitation events in the recent past. Thus, as scientists, they can show them where possible what the extent of a projected future impact may look like if there's not resilience built into their systems. For the Minneapolis audience, there were a number of recent events that matched the scale of the projections that scientists were positing about the future, such as the Duluth event in 2012, which was close to 8 inches in 24 hours, but exceeding 14 inches by the time the storm had passed. It resulted in the St. Louis River cresting at a historic high of 16.6 feet, with damage costs in the range of $108 million for the region for this just single storm. Thus, is it the role of the scientist to frame a projected future in a manner so that the consequences are put forward if the science is not heeded to and no action is taken? For example, this was a study done in southwest New Hampshire. This particular road crossing was considered undersized for a climate change mediated future design storm. The cost of upgrading this particular infrastructure to make it resilient was in the range of $56,000. Well, it so happened that subsequent to the report being made to the city, the amount of rain projected for this climate-mediated design storm actually occurred. Now, this was happenstance, and the scientists doing the study realizing that this single extreme event communicated to the press that it was just the weather, not climate change. But it did show that the community did not consider the likelihood of future impacts. The cost could significantly increase. In the case, this damage of this undersized system was 100% more than being precautious and building a more resilient system in place. And if we go back to the initial point made in this introduction, often the risk for a community is related to the costs in life and infrastructure. So, do you agree that scientists cannot judge for a community what the risks the community is willing to live with? That this is a political question, not a scientific question. We will return to this in the last week of the course.